What's up, pre-calculus students? Mr. Messner, Red, doing a video here. So we have these rational equations. Like the last set of inequalities you did with polynomials. Kind of know what the shape of polynomials look like. These, we don't know. But we do know that they got some interesting points, like where they could change sign, okay? And in the notes, we talked about zeros and asymptotes. So these inequalities have asymptotes, and asymptotes are like these imaginary lines where a function may approach but not cross over. And this occurs when you end up with a zero in the denominator, or you have like a number over zero in a function. Now, why is that the case? Think about like a number like 5. Now, it's not 5 over 0, but let's get something close to 0, 0.1. 5 divided by 0.1, if you do that in a calculator, it's 50. And if you do 0.01, it becomes 500. 0.001 becomes 5,000. 0.0001, 50,000. So you can see like you'd get bigger and bigger and bigger values. And then you could have a situation where you might have like a negative, and then it'd be bigger values, but negative values. So these are where we could possibly change signs. Now, you don't always change signs at asymptotes. Sometimes you go up and then you come back from going up. But it's a possible location where we change signs. Asymptotes, and then also just like polynomial zeros, where you cross through an axis and it's like positive values to negative values. And that's where we're going to be able to go, because we're trying to find when we're greater than 0 or less than 0 for most of these problems, like above the x-axis, below the x-axis. And we're going to start by doing the ones with the zeros first, and then we'll do the other ones because they're trickier. All right, we want to take the numerator equal to 0. These are going to be my zeros. And then we'll take the denominator equal to 0. These are going to be when we're undefined or where we have potentially an asymptote. Now, there are situations where if your numerator and your denominator are 0, you have holes in your graph. So like a 0 over 0, you end up with a hole. And I'd be able to show you that if we see one. Okay, so after we do this and we throw it on a number line, just like we did with the polynomials, what's the key thing about these is like you don't know what the graph looks like. So I'm not going to like try to graph this because I don't know. Now we could if we wanted to, but easier way to do it is to just use test points. Understanding that if we've exhausted all of our zeros, if I just test one point in an interval, I'll know all of the signs in my interval, or else they would be another 0 or another asymptote. It helps to plug in test points into a factored form. That way we're just multiplying and dividing rather than adding. So plug things into this like a 1 or a 0. Positive, 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 positive. Positive divided by positive times positive is positive. -3. Positive, positive, negative. So you think of positive divided by like a negative times positive, positive over negative. -5. Positive, negative, negative. Positive, negative, negative. That ended up being a positive. -7, negative, negative, negative. And you see like they flip signs. They won't always flip signs. Multiplicity sometimes has to do with it as well here, where if we know it's a multiplicity that's even, it bounces or doesn't change sign. For example, like 1 over x squared. You say like x equals 0, but the multiplicity is 2. What you'll find in the graph of 1 over x squared is that you don't change signs at your asymptote. It's the same. Why? It's like, okay, the multiplicity of that asymptote is like 2. You can kind of think of it that way. Anyways, now we're looking for when we are bigger than or equal to 0. I've done the sign analysis. Now, it's very important. -6, -4, -2, they're not all 0. It's just the -6 that's the 0. -4 and -2 are when we have an asymptote or we don't have a defined function value. So we're finding our intervals, including the zeros. We're only going to include -6, but we're not going to include -2 here. So I would say x is bigger than or equal to -6, less than -4, or greater than -2. And then set notation, x belongs to -6 to -4, or -2 to infinity. All right, skip number 2. We'll come back to that. Let's look at number 3. x plus 3 equals 0, x equals -3, x minus 2, x minus 3 is the denominator equal to 0, x equals 2 and 3. So number line, -3, 2, and 3. Let's look at our factored form, x plus 3 over x minus 2, x plus x minus 3. Plug in 4, positive, 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 positive. Plug in 2.5, positive, positive, negative. It's negative. Plug in 0, positive, negative, negative. Plug in -5, negative, negative, negative. Okay. We're looking for less than or equal to 0. Maybe good thing to say, okay, that's the 0. When the numerator is 0, 0 over a number is 0. A number over 0 is undefined. It's important to remember that. You're not allowed to divide by 0, but 0, any number into 0 is 0 times. This is undefined. This is undefined. Less than or equal to 0 includes this. Will not include the 2 or the 3 there. So less than or equal to -3 or between 2 and 3. Set notation is negative infinity to -3, 2 to 3. All right, let's look at number 4. Numerator, x plus 3, x minus 3 is the factor numerator. It's a difference of squares. Denominator, x minus 5. So I get -3, positive 3, positive 5. These are zeros. This is undefined. Throw those down. -3, 3, 5. Looking at x plus 3, x minus 3 in the numerator over x minus 5, just to help me with the test points. Look at something like 5, not 5, 6, 7, positive, positive, positive. Look at something like 4, positive, positive, negative. Look at something like 0, positive, negative, negative. Positive, negative, it's a negative divided by negative, positive. -4, negative, 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 that's a negative. It's less than 0, so I don't really have to worry about the fact that this is a 0, this is a 0, and this is when we're undefined. You instead just worry about when we are less than 0, or negative values. So x is less than -3 and greater than 3, less than 5, or x belongs to -infinity, -3, 3, 5. All right, let's look at 6, 10, and then we'll go back to the ones and numbers. All right, numerator equal to 0. X squared plus 1, does that equal 0? Subtract 1, that's a -1. The square root of a -1 is imaginary. You don't get any solutions from that. 2x minus 5, you can solve to get x equals 5 halves. Add 5 divided by 2. X plus 1 cubed, obviously you get x equals -1. X minus 1 squared, and here's where the multiplicity comes into play. X equals 1. So I'm going to throw down -1, 1, 5 halves. Plugging it into this, understanding x squared plus 1 is always positive because it's like a value squared is positive plus 1 is positive. Plug in something like 5, positive, 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 positive. Now watch this. Like, let me show you how multiplicities work. 5 halves, multiplicity is 1. It's going to pass through. 1, the multiplicity is 2. It's going to bounce. Or it's going to reach an asymptote, and then on the other side be coming in the same direction. -1 has a multiplicity of 3. It's going to bend through, but it's going to go through. So it's going to be positive. Let's double check. Ready? Let's plug in something like 2. positive, negative, positive, positive. Okay, let's plug in something like 0, positive, negative, positive. Okay, 0 minus 1 is negative, but squared is positive, so it's the same thing. So it doesn't change signs there because of the multiplicity. And negative 3, positive, negative, negative, positive. Because that's square. So right there. When are we less than 0? I don't care about the endpoints. It's just going to be here. But what's really important is that this is at 1. This is an undefined value. So I would not include 1. So when we do our intervals, we're going to have to do bigger than -1, less than 1, bigger than 1, less than 5/2, like that. Or set notation would be a little quicker. -1 to 1, 1 to 5/2. 10 is like the same thing. Really easy to see this one. -3, 5. Multiplicity of -3 is 2. Both of these are asymptotes. So 5, let's start with something like 6, positive, positive, positive. All these leading coefficients are positive, which is why it's happening like this. Pass through, because the multiplicity is 3. It's like bending through. But a -3, multiplicity is 2. It's not going to change signs. Boom, negative. Double check, -4. -4 plus 3 squared is a positive. -4 minus 3 cubed is a negative. That's a negative. Okay, so when are we less than 0? Here and here. I'm not going to write down the intervals. You can figure it out. All right, what if we got something other than a number? And for all of these, with the zeros, we're always thinking like, when are we above or below y equals 0? But now this is like 2. So when are we above or below y equals 2? Doesn't seem obvious, and it's not. There are multiple ways to do this, and I'm going to kind of work through both of them. We like zeros, positive, negative things. So what I would recommend doing, and we did this with polynomials, is like move everything to one side. And when I subtract 2 from both sides, I get 0 left over on that side. And now we solve this set equal to 0. But like, how do I solve this set equal to 0? Well, you're gonna need to combine these two things, this and this. And you can multiply the top of this by x plus 2 and x plus 2. So pretending this is like 2 over 1. Give it the same denominator as this. You have to multiply the top and the bottom, so you don't change it. It's just a version of 1. You're allowed to multiply things by 1, and it's not going to change it. And that will enable you to take these things and combine them. And now I can distribute this, and this is 2x plus 4. But let's be careful. When I'm ready to add or really subtract these two things, it's 4 minus the quantity of 2x plus 4. A lot of students make mistakes on that. And that's got to be greater than 0. Okay, now I have a situation after simplifying this one extra step to be -2x over x plus 2, where I can see when is my numerator equal to 0, when is my denominator equal to 0. And that's going to be at 0 and at -2. Now, I'll show you another way to do this, but I'm not sure if it's going to work as well as I think. All right, now, I wish I could pause this. I can't. Yes. Okay. I'll free it up for you. Which quiz was it? Which period are you in? Okay. Okay, you should be good. Okay, so where were we? Plugging in something like 1, I got a negative over a positive. Negative. Plugging in something like -1. That'd become a positive. -2 times -1 is a positive. -1 plus 2, that's a positive. So positive over positive, positive. And then -3, positive, negative, negative. Again, multiplicities are 1 and 1. So if you answer when are we bigger than 0, it's right here. Now let's see if we can do this a different way. Okay. Or, and I'm not going to show you the interval. What if you try to solve it like this? How do I get that? Well, I can multiply both sides by x plus 2, and I get 4 is greater than 2x minus 2 plus 2. 2x plus 4. This doesn't work out. Because if like you subtract 4, you get when is 2x greater than less than 0, which is going to be when x is negative. But it's not, because if I switch over -2, if I look at -3, like 4 over -3 plus 2. No. Yeah. If I solve this, I get any negative number. But if I look at something like -3, I get 4 over -3 plus 2, which is -1, and that's -4. That's definitely not bigger than 2. But it, like -1, 4 over, yep, -1 works. It didn't work. It should be between 0. What did I do wrong here? I should be thinking about values that are between 0, not including 0, and +2, not -2. I'm gonna look at the key real quick. No, that's only got -2 to 0, but why am I thinking that's wrong? Oh my goodness. It's not going to be, I was fine. I was fine the entire time. If I plug in -1, this becomes 1. That becomes 4 divided by 1. That's fine. If I plug in something like 0.1, it's 2.1. 4 divided by 2.1 is going to be less than 2. I was fine. This is what you want to do. Don't want to do it this way. It's not going to work the way the fact that we have this potential asymptote in the original thing makes things complicated. Okay, so move everything onto one side, common denominator, like this. Add the 1, common denominator. How do you get a common denominator with 1 and 3 over x minus 4? Multiplied by x minus 4 over x minus 4, pretending that 1 is a 1 over 1. Now it's a plus, thank goodness, because if it was a minus, it'd be minus this entire thing. It should be plus that entire thing, but the parentheses don't matter when you're adding things. Don't try to distribute like the 3 into the x and the 4. So this is x minus 1 over x minus 4 is less than or equal to 0. The numerator, the denominator equaling 0. Number line 1 and 4. Positive to the right of 4, positive over a positive. 3, positive over a negative. Negative 1, negative over a negative. When are we less than or equal to negative 1 at the beginning? It's the same as when this is less than or equal to 0. Between 1 and 4, are we including 1? Are we including 4? Well, 1 can be included because that's the numerator equal to 0. That's when we 0. But 4 can't because that's when it's undefined. Plugging in 1, 3 over negative 3 is negative 1. So I won't write the intervals again. You're including the 1. You are not including the 4. You got multiple things going on like this. Well, get everything onto one side. How do you do it? Subtract. I'm going to subtract this entire thing so it ends up on the other side. Greater than 0. How do you combine these? They need common denominators, but it's not like you can just like add 1 to the bottom and the top. Not allowed. You're not allowed to add 1 over 1. That's not like, that's going to change things. You're adding something to this side, but you're not adding it to that side. Okay, that's adding 1 to just the left side. And obviously you can't just like add something into a denominator. So you need a common denominator, which means you got to multiply both sides by the other's denominator. X minus 1 times x plus 2. X plus 1 times x plus 2. So I got to multiply this guy. It's x squared plus 2x. I got to multiply this guy. X squared plus x. You're going to subtract them over the common denominator when I combine them. X plus 1, x plus 2. That's greater than 0. Simplify the numerator. X squareds go away. 2x minus x is just 1x. When is that greater than 0? Okay, so we have numerator equal to 0. That gives me the x equals 0. And then denominator, negative 1, negative 2. Hope I finish this before the next class. This is a 0. This is undefined. This is undefined. This equation is the same as this equation, greater than 0. So we're looking for greater than 0. Okay. All multiplicities are 1. You start to the right of 0, you see it's positive, positive, positive. So positive, and I'm going to change signs because the multiplicities are 1. You can double check that. When are we greater than 0? Here and here, including here. Let's just use quick set notation, negative 2 to negative 1. 0, including 0 to infinity. Okay, this guy. Thank goodness. You would think it would be nice and ready to go, but it's not. You got to subtract the 10, get everything onto one side. This needs a common denominator with this. X minus 5 over x minus 5, if this is 10 over 1. This is x squared plus 3x minus 40 over x minus 5 minus 10x minus 5. You can distribute the 10. It's 10x minus 50 over x minus 5. Now, since we're subtracting this, you got to distribute the negative. So this would be x squared plus 3x minus 40 minus 10x. 3 minus the 10x is negative 7x. And negative 40 minus negative 50 ends up being plus 10. Negative 40 minus negative 50 is negative 40 plus 50. That's over x minus 5. We do that because, look at this, I can factor this numerator. This is x minus 5, x minus 2. Denominator is x minus 5. Aha! We have a situation where 5 will be a location of like a hole. Now, holes mean like we may or may not change signs depending on the location. The reason why it's a hole is because like whatever number I plug in for x, this will always cancel out. And just x minus 2 is going to dictate what the graph looks like. But I can't plug in 5 because if I plug in 5, I got like 0 over 0 kind of thing. So anyways, what I'm trying to tell you is we need to just check. Don't assume the multiplicity is 1. It's kind of like happening twice. Watch. If I plug in 6, positive, positive, positive. 5 is undefined. You're not allowed to divide by 0. It's not a 0. 2 is a 0. Let's plug in 3. Negative, positive, negative. Negative, positive, negative. Okay, that's a positive. Plug in 0. Negative, negative, negative. That's a negative. So we end up not changing signs at that hole's location. Want to be greater than or equal to 0, including 2, not including 5, all of those values. All right. I feel like these I can, as long as I keep track of negative 7. I feel like I could have done it here. Like when I just have to make sure like I understand negative 2 is a solution. But if I multiply by x plus 2, I get 2 times x plus 2. This is where I get 0. And as long as you put negative 2 and 0 down, it works out. Let me show you. This 4. Okay, 4 is important because it's the denominator equals 0. We can change signs with that. But you can multiply both sides by x minus 4. You get negative x plus 4. Okay, now be careful here. Let's add the x maybe, because like, let's say I subtract the 3, I get negative 1 is less than or equal to negative x. Remember from like algebra 1, if you divide by a negative, you have to flip the sign. But look, 1, 4, 1 and 4. Do your sign analysis. That's the problem is like the sign analysis would be tricky if we did it this way. It's because like I'd have to pick like a value like 5 and then do 3 over 5 minus 4. Is that less than or equal to negative 1? It's actually a little bit more complicated than just figuring out if it's positive or negative. Plugging in 3 over 3 minus 4, is that less than or equal to negative 1? That's, I think, trickier. So this is why I probably advise you to do the whole 0 method. Zeros are nicer to handle. All right. Now, is it fun? No. Like, would you prefer to say, okay, negative 7, and then multiply both sides by x plus 7, you get x squared plus 2x plus 19 is less than 3x plus 21. And then you can subtract and subtract, and you get x squared minus x minus 2 is less than 0. You're like, oh, sweet, x minus 2, x plus 1. And you get 2 and negative 1. But then when you go back and try to plug it in, it's not about being positive or negative. It's about being greater than or less than 3. And that is not fun. And it's probably going to take you the same amount of time to do this than it would if you just did the common denominator method. So that's that. Subtract the 3, common denominator, so that we can check our signs. Multiply the top and bottom of this by x plus 7. When we distribute the 3, make sure you either distribute the negative 3 or rewrite as x squared plus 2x plus 19 minus the quantity of 3x plus 21 over the common denominator. That's a 21, not a 4. Then I got x squared minus x. That's a minus 3x, and a minus 21 becomes minus 2. This is kind of just like what we saw. Factor, I get x minus 2, x plus 1 over x plus 7. So 2, negative 1, and negative 7. Looking at this, positive, 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 multiplicities. Not sure. You should probably double check. Maybe negative 5, negative, negative, positive. Okay, that's fine. Okay, works out. Less than 0, negative 1 to negative 2, less than negative 7. Which one are our zeros? 2 is a 0, so I need to include 2. And negative 1 was a 0, so I need to include. Oh, I don't include. Never mind. We're less than, so you don't have to worry about the zeros. So just less than negative 7 and negative 1 to 2. All right. Same deal with solving equations. Only problem is here, I don't want to worry about denominators equaling things. Like 5, I get 26 over 0. That's not 0, that's undefined. So it's like, oh, x squared plus 1, when does that equal 0? That doesn't equal 0. You get an imaginary number. We're sticking with the reals. So does not exist is the answer to this first one. Great one to start off with. The other ones, since it's an equation, it actually is easier to do the alternate way that I showed you. Let me show you what I mean. Instead, like, look at 14. Instead of moving everything onto one side, like multiply both sides by each other's denominator. Like multiply both sides by x plus 1, x plus 1. And it's like, okay, those are gone. You just have 3x equals 2x minus 1. Subtract 3x, you get x equals negative 1. It's tricky, actually. You think this is the solution, but it's not, because negative 1 plus 1 is 0 in a denominator. And you don't want that. So there's actually no solution to this. You can also check that by moving everything onto one side instead of equal to 0. You get 2x plus 1. No. 3x minus 2x is just x plus 1 over x plus 1. Does that equal 0? No, it doesn't equal 0. So it does not exist for this one. Oof. 15. All right, watch. Multiply both sides by x plus 5. It's essentially cross-multiplying, but I don't like to say cross-multiply because students try to cross-multiply everything. Multiply both sides by 9 minus x. Okay, why do I do that? Because like 9 minus x just moves everything onto the same level. 2x minus 3 times x plus 5. It's 2x squared. That's a 10x. This is a negative 3x, so that's a 7x. And that's minus 15. Add an x, subtract a 9. I get 0 equals 2x squared plus 8x minus 24. Factor out a 2. That doesn't work. No, it's not 6, it's 12. Yes, it works. X plus 6, x minus 2. Honestly, it's probably easiest to get a common denominator than multiply both sides. So 2 plus x, 2 plus x, 2 minus x, 2 minus x would give both sides a common denominator. I'm going to distribute, that's 6 plus 3x. This is 6 minus 3x over 2 plus x times 2 minus x. This might be another no solution. Yeah, because the numerator is going to be, let's find out. This is 12 in the numerator. The denominator is 2 plus x and 2 minus x. That distributes to be 4 minus x squared. Multiply both sides by that 4 minus x squared. This is easier than if we move the 4 over, in my opinion. It's 16 minus 4x squared. Subtract the 16 from both sides, you get negative 4 equals negative 4x squared. You get x squared equals 1. X equals plus or minus 1. Does that work? 3 over 1 plus 3 over 3. It's 3 plus 1. 3 over 3 is 1 plus 3 over, plus or minus 1 actually works. That's tricky. That's a good one. It's the last problem I'm doing. I'm not doing 17, 18, 19, 20, 21, 22, 23 because we don't have to. Okay, 17 through 20. It's going to be a while. It's going to be stressful doing those. And then 21, 22, 23, we'll do more in the next class. So, common denominator, 4x over x plus 1 over x equals 30 over 6x. Multiply everything by x if you want to. You can combine these two. This is like 4x plus 1 over x equals 30 over 6x. Like if you multiply both sides by x, x cancels here and the x cancels here, giving you 4x plus 1 equals 30 over 6. That's 5. Subtract 1, divide by 4, x is 1. 4 plus 1 is 5, equals 30 over 6, which is 5. So what did I just say? Inequalities, don't solve it like the first way that I solved it, because you have to first remember that the asymptote could change things. And it's hard to check to see if you're greater than or equal to a number. It's easier to check if you're greater than or equal to a 0. But for equations, you don't have to worry about checking things. For equations, you can just find the answer. Do it the easiest way possible, which means it could mean like just moving everything up, multiply everything by like each other's denominators, like this situation. Lots of different things. Some good questions here, some tough questions here. Good luck out there.